Good morning. This is the part 3 of the lecture on Module 2 CET203 Fluid Mechanics and Hydraulics for second year civil engineering students of APJ Abdul Kalam Technological University. And today we are going to discuss about the kinematics of fluids. So kinematics, as you know, is the study of fluids without considering study of the motion of the fluids without considering the forces acting on the fluid. So we'll be proceeding with that. So kinematics deals with motion of fluid particles without considering the forces that cause the motion. So there are two methods of describing fluid motion. One is the Lagrangian method and the second one is the Eulerian method. So let us discuss the difference between these two. In Lagrangian method, a single fluid particle is followed during its motion and its velocity, acceleration, density, etc. are described. So we are going to follow a single fluid particle, and in its path we are going to describe its properties like velocity, acceleration, density, etc. And this will help us understand the motion of the fluid, and this is known as the Lagrangian method. In the Eulerian approach, the velocity, acceleration, pressure, density, etc. are described at a point in a fluid field. So we are going to stand at a point and we are going to describe the velocity, acceleration, pressure, density, etc. of the fluid particles that are going to pass through that particular point. This is known as the Eulerian method. So the Eulerian method would be a much more simpler method compared to a Lagrangian method. And so in this course, we will be following the Eulerian approach. Now, fluid flow can be classified into 6 different categories: steady and unsteady flow, uniform and non-uniform flow, laminar and turbulent flow, compressible and incompressible flow, rotational and irrotational flow, and one-dimensional, two-dimensional, and three-dimensional flow. So these are the 6 different types of flows that fluid flow can be classified into. Now many of these might look similar to you. For example, steady flow and uniform flow. So for a layman, steady flow and uniform flow does not mean different things. But for a person who studies fluid mechanics, steady flow is totally different from uniform flow. So we will see what each of these mean and how fluid flow is classified into these categories. So steady flow and unsteady flow. If at any point in a flowing fluid, the various fluid characteristics like velocity, pressure, density, temperature, etc. does not change with time. That is, you're standing at a point and you're describing the fluid characteristics like velocity, pressure, density, temperature, etc. at that particular point at different time intervals. And you notice that as the time progresses, the properties are not changing. That is, the properties of the fluid do not change with time. Then that type of a flow is known as steady flow. So if you are to mathematically represent steady flow, the differential of the fluid characteristic like pressure, velocity, density, temperature, etc. with respect to time can be taken to be equal to 0. So that is the mathematical representation of steady flow. Any fluid characteristic, if you are differentiating with respect to time, it will become equal to 0. That is, it is independent of time. Now, unsteady flow, if at any point in a flowing fluid, the various fluid characteristics like velocity, pressure, density, temperature, etc. changes with time, it is known as unsteady flow. That is, if you're differentiating a fluid characteristic with respect to time, it will not be equal to 0. So steady flow and unsteady flow have got to do with time. Whether the characteristics change with time or do not change with time, that is how you're going to differentiate between steady flow and unsteady flow. Moving on to uniform flow and non-uniform flow. Uniform flow is when, if at any instant of time, the various fluid characteristics like velocity, pressure, density, temperature, etc. does not change with distance. So here imagine that number of people are placed along the flow at different points, and they are asked to measure the velocity, pressure, density, temperature, etc. at their respective points. There are 5 people standing at different positions along the flow, and they are asked to measure the density, velocity, pressure, temperature, etc. at the point at which they are standing. at a particular instant of time. And they noticed that all their characteristics have the same value. That is, velocity at point A will be equal to velocity at point B will be equal to velocity at point C, like that. Temperature at point A will be equal to temperature at point B will be equal to temperature at point C, so on and so forth. So it does not change. The fluid characteristic does not change with the distance. That is known as uniform flow. If you want to mathematically represent uniform flow, it can be represented as dou of the fluid characteristic divided by dou S is equal to 0. S standing for displacement or distance. So fluid characteristics are independent of distance, and when you are differentiating any fluid characteristics, let it be velocity, temperature, acceleration, anything, so dou V by dou S, dou rho by dou S, dou P by dou S, everything becomes equal to 0 because they do not depend on distance. Non-uniform flow would be if at any instant of time the various fluid characteristics changes with distance. That is, they do not, they depend on the distance. As you move forward, the properties seem to change. So that is known as non-uniform flow and can be mathematically represented as dou of the fluid characteristic with respect to dou S is not equal to 0. So this is the difference between uniform flow and steady flow. In steady flow, the flow characteristics does not change with time. Whereas in uniform flow, the flow characteristics do not change with distance. Next, we move on to laminar and turbulent flow. This is one of the known ones. That is, you might have even discussed this while you were at school. Laminar flow is when the various fluid particles move in layers or laminae, with one layer of the fluid sliding smoothly over an adjacent layer. So you can see here that the fluid particles are moving smoothly one layer over another. They are moving one over another very, very smoothly. That is known as laminar flow. In turbulent flow, when the fluid particles move in an entirely haphazard or disorderly manner, that results in a rapid and continuous mixing of the fluid, leading to momentum transfer as flow occurs. So it is a very disorderly flow when you're talking about turbulent flow. So this is turbulent flow and this is laminar flow, and there is a particular dimensionless number that can be used to differentiate between laminar flow and turbulent flow, that is known as the Reynolds number. And everybody might be familiar with how Reynolds number can be used to differentiate between laminar flow and turbulent flow. So there will be a threshold value. If the Reynolds number is lesser than the threshold value, it is laminar flow. If it is greater than that threshold value, it will be turbulent flow. And that threshold value, it actually differs for different types of flow: groundwater flow, surface flow, pipe flow, etc. That value keeps changing, so that is why I have not mentioned it here. However, Reynolds number is the number that can be used to differentiate between laminar flow and turbulent flow. Next, it is compressible and incompressible flow. So when we are talking about compressible, naturally the property that comes into our head is the density. So incompressible flow is a flow in which density of the fluid changes from point to point. So whenever we think about density, we usually think about it as constant. That is not true. The flow density can change from point to point, and when it does, that is, the density is not constant, that particular fluid is known as a compressible fluid, and that particular flow is known as a compressible flow. That is, and an incompressible flow is a flow in which density does not change from point to point. That is, density is a constant for incompressible flow. So when we are talking about water, this is the fluid which civil engineers usually deal with. We are talking usually about incompressible flow. We consider water to be incompressible. Next is rotational and irrotational flow. In rotational flow, is the flow in which fluid particles, while flowing along the streamline, also rotates about their own axis. And irrotational flow is when flow in which fluid particles do not rotate about their own axis. Whereas the rotational component, when it is there, it is known as a rotational flow. If fluid particles do not rotate about their own axis, it is known as irrotational flow. Next, we have one-dimensional, two-dimensional, three-dimensional flows depending on the number of dimensions on which the velocity of the flow is dependent. If the velocity of flow is a function of one space coordinate, which is x, then it is known as a one-dimensional flow. When the velocity of flow is a function of two space coordinates, say x and y, then it is known as a two-dimensional flow. And when velocity of flow is a function of three space coordinates x, y, and z, then it is a three-dimensional flow. So there are three types of flows: one-dimensional, two-dimensional, and three-dimensional. Actually, there are an infinite number of dimensions in space. At our level, we are only going to consider up to three-dimensional flow: one-dimensional, two-dimensional, and three-dimensional flows. Now, flow, when we are considering motion of the fluid, or the flow of the fluid, it's a very abstract phenomenon, and we need to use certain approximations in order to understand the motion of the fluid. And so we use that to draw flow pattern. So flow patterns can be described using imaginary lines or patterns. Some of them are streamline, stream tube, path line, and streak line. So these are imaginary lines or imaginary paths, and we use them to describe the fluid motion, because fluid motion is a very natural phenomenon and it is difficult to describe them mathematically without the help of any imagination. And so we are going to use certain imaginary lines or patterns to describe the fluid flow, and such streamline, stream tube, path line, streak line, etc. are these imaginary lines that can be used to describe the motion of the fluid. So let's start with streamline. Streamline is an imaginary curve drawn through a flowing fluid in such a way that the tangent to it at any point gives the direction of the velocity of flow at that point. So it's an imaginary curve drawn through a flowing fluid in such a way that the tangent to it at any point gives the direction of the velocity of flow at that point. So I'll describe this to you. This is the figure. So you can see these blue lines are showing the direction of velocity of flow at different instants. Direction of velocity of flow at different instants. And we are going to draw a red line that connects these tangents. It's the locus of these tangents. And this red line is known as a streamline. Okay, it's an imaginary curve drawn through a flowing fluid in such a way that the tangent to it at any point gives the direction of the velocity of flow at that point. So at this point, this is the velocity and this is the tangent. At this point, this is the velocity and this is the tangent. So when you connect these tangents, the locus of these tangents, you will get a streamline. Or basically, streamline is the direction in which the flow is taking place, because we are getting a streamline by connecting the tangents to direction of velocity at all the points. So basically, a fluid flows along a streamline. So these red lines are your streamlines. So here in the figure, the red lines represent the streamline and the blue arrows are the direction of the instantaneous velocities. So since the streamline is always tangential to the fluid flow, so fluid flow is taking place along the streamline, there will be no component of velocity perpendicular to the streamline. That is, flow cannot occur across the streamline, because by the basic definition of the streamline itself, a streamline is drawn by plotting the tangents to the velocities of the points at each location. By connecting the tangents, we get our streamline. So basically, streamline is happening along the flow. This means that once the streamline is drawn, we can be sure that flow does not occur across a streamline. Flow only occurs along a streamline. Next is stream tube. Now, stream tube is an imaginary tube comprising of and bounded by streamlines. Now, stream tubes are usually helpful in derivations. What we are going to do is we are going to bundle up certain streamlines and make a tube out of it inside the fluid, and we're going to call it a stream tube. So here you can see streamlines are there, and we're going to bundle them up in the form of a tube. So this is a tube that comprises of and is bounded by streamlines. Okay, and this is known as a stream tube. So flow takes place through a stream tube and flow does not occur across a stream tube. Basically because stream tube is composed of streamlines. So since flow takes place only along the streamlines, flow cannot take place across the stream tube. Next is path line. The path line is the simplest flow description pattern of all of them. It is the path or the line traced by a single fluid particle as it moves over a period of time. So if this is the path of the fluid particle at t equal to t start, and this is the path of the fluid particle at some intermediate time, this is the particle at end, and the path followed by the particle. So this is basically the path line. Now path line can also have these loops coming in between, depending on how the fluid particle is moving. In steady flow, that is when the characteristics of the fluid do not change with time. Streamlines and path lines will coincide. Next is streak line. Now, streak line is actually an experimental line. So usually in experimental work, we insert a dye or a color into the flowing fluid in order to trace the path of the moving particles. And the line traced hence is known as a streak line. Now, it's also called a filament line, a streak line or a filament line. Now, I'll just show you how a streak line is formed. So this is a pipe through which flow is taking place, and the red spot here corresponds to the color or the dye that is going to get inserted into the flow. And any fluid particle coming out of the pipe will now be colored red due to the color or the dye injected in between. So let this be the first fluid particle that comes out, and this blue line is the path line of the fluid particle. At t equal to 0, the fluid particle reaches the color or the dye. Now tracing the motion of the fluid particle, at t equal to 1, the fluid particle reaches here. At t equal to 2, the fluid particle reaches here. At t equal to 3, the fluid particle reaches here. And at t equal to 4, the fluid particle reaches here. And at t equal to 5, the fluid particle reaches here. So this is the path line of a fluid particle that passes through a color or a dye. This is the first particle. Now the second particle passes through the pipe. Now let us say that the second particle is behind the first particle and reaches the color or the dye at t equal to 1. That is, when the first particle is over here, the second particle reaches the color. Then at t equal to 2, the particle is over here. T equal to 3, the particle is over here. T equal to 4, the particle is over here. At t equal to 5, the particle is over here, so on and so forth. This is the third fluid particle which comes behind the second fluid particle, and thus the third fluid particle reaches the color or the dye at the time t equal to 2. That is, when the first fluid particle is over here, and when the second fluid particle is over here, the third fluid particle reaches the color or the dye. Now correspondingly, the position at t equal to 3, t equal to 4, t equal to 5, so on and so forth. This is the fourth fluid particle, and it reaches the color or dye at time t equal to 3. So at t equal to 4, it is over here, at t equal to 5, and so on and so forth. And the next fluid particle reaches the color or the dye at time t equal to 4, and now it is here at t equal to 5, and so on and so forth. Now in order to plot the streak line, what I'm going to do is I'm going to join all the points corresponding to the same time. So when you take t equal to 1, the beginning of the second fluid particle and this point of the first fluid particle can be joined. This is a streak line. When you take t equal to 2, the beginning of the third fluid particle, these particular points of the second fluid particle and the first fluid particle can be joined. When you take time t equal to 3, beginning of the fourth fluid particle and the t equal to 4 of the other fluid particles. When you take t equal to 5, sorry, this is t equal to 4, and similarly when you take t equal to 5, you will get these lines. So these red lines that you see here that is obtained by joining the same time is known as a streak line or a filament line. Okay, the red lines indicate the path traced by the dye at different times. So at t equal to 1, the dye looks like this. At t equal to 2, the dye looks like this. At t equal to 3, the dye looks like this, and so on and so forth. So these lines are visible. These red lines are visible to us. These blue lines are the path lines that are not visible to us, but the red lines, that is the color traced by the dye, is what is visible to us, and these red lines are called streak lines. Next we move on to velocity and acceleration of fluid flow. So let capital V be the velocity of flow in a fluid field. So I am writing it in terms of the three components I, J and K. So capital V can be given by Ui cap plus Vj cap plus Wk cap, where U is the component of velocity in the x direction, which is a function of all the three space coordinates and time. So U is a function of x, y, z and time. V is the component of velocity in the y direction, Vj cap, small v, and V is also another function g of x, y, z and t. That is the function of all the three space coordinates as well as time. And w is the component of velocity in the z direction, where w is another function of x, y, z and time. The resultant velocity or the magnitude of the velocity can be obtained as square root of u squared plus v squared plus w squared. Now, to determine the acceleration of the fluid particle, acceleration in the x direction, let it be ax. Ax is given by du by dt, where u is the velocity component in the x direction. But the problem with this is that u is a function of three space coordinates and time. And so a total derivative of u with respect to time is actually not very easy. U is a function of x, y, z and time. So du by dt cannot be directly found out. We have to use or make use of partial differentiation here. So du by dt can be expressed as dou u by dou x into dx by dt plus dou u by dou y into dy by dt plus dou u by dou z into dz by dt plus dou u by dou t into dt by dt. So here you can see that all the dependencies, u is dependent on x, u is dependent on y, u is dependent on z and u is dependent on time. All those have been given a partial derivative and multiplied by a total derivative into dx by dt, into dy by dt, into dz by dt and into dt by dt. This is how total derivative of a function that is dependent on a lot of variables is actually expanded. Now dx by dt is nothing but u, dy by dt is nothing but v, dz by dt is nothing but w and dt by dt is 1. So rearranging, I will be able to get ax as equal to u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. This is ax. Similarly, I will be able to find out the acceleration components in the y and z directions. So acceleration in the y direction, let it be ay, which is dv by dt, which can be written as dou v by dou x into dx by dt plus dou v by dou y into dy by dt plus dou v by dou z into dz by dt plus dou v by dou t into dt by dt. Exactly how we had expanded du by dt, here we are expanding dv by dt. Now dx by dt, dy by dt, dz by dt and dt by dt are known. So replacing ay can be written as u dou v by dou x plus v dou v by dou y plus w dou v by dou z plus dou v by dou t. And similarly, direction acceleration in the z direction is z, which is dw by dt can be expanded in a similar fashion, and we will end up getting u dou w by dou x plus v dou w by dou y plus w dou w by dou z plus dou w by dou t. The resultant acceleration is given by a is equal to square root of ax squared plus ay squared plus az squared. Now we'll discuss about the concept of convective acceleration and local acceleration. So this is the formula for ax, acceleration in the x direction, ay and az. You can see the similarities in the three accelerations. Actually, if one acceleration is known to you, the others can be easily deduced from the same. Now, this particular component of ax, u dou u by dou x plus v dou u by dou y plus w dou u by dou z, where the acceleration is obtained by differentiating with respect to space, is known as convective acceleration. And that part of velocity, when differentiated by time to obtain acceleration, dou u by dou t, is known as the local acceleration. So there are two types of acceleration in ax. Convective acceleration, wherein acceleration is dependent on the velocity, on the space, and local acceleration, wherein the acceleration is dependent on the time. Similarly, ay and az also have convective acceleration and local acceleration terms. So dou v by dou t and dou w by dou t are local acceleration terms, and u dou v by dou x plus v dou v by dou y plus w dou v by dou z is convective acceleration term of ay, and u dou w by dou x plus v dou w by dou y plus w dou w by dou z is the convective acceleration term of az. Moving on to numerical problems. The velocity vector in a fluid flow is given by the formula, capital V is equal to 4x cube I cap minus 10x squared by j cap plus 2t k cap. We are asked to find out the velocity and acceleration of the particle at the point 2, 1, 3 and time t equal to 1. So here capital V is given as 4x cube I cap minus 10x squared by j cap plus 2t k cap. So we can find out the components u, v and w from here. U is 4x cube, v is minus 10x squared y and w is 2t. The first question is asking us to find out the velocity at a point 2, 1, 3, which is very simple because the expression for velocity is given to us. All we need to do is substitute. And so at the point 2, 1, 3 and t equal to 1, u is given by 4 into x cube, that is 4 into 2 cube, which is 32 I cap. V is given by minus 10x squared y, so minus 10 into 2 squared into 1, which is minus 40 j cap. And w is given by 2t, where t is equal to 1, so w is 2 into 1, that is 2 k cap. So u, v and w terms are known. If you want to find out the magnitude of v, it is given by square root of u squared plus v squared plus w squared, which comes to square root of 32 squared plus minus 40 the whole squared plus 2 squared, which comes to 51.26 units. So this is the resultant velocity. The next one is asking us for resultant acceleration. So we are going to use the formula that we know of ax, ay and az. To determine acceleration, we will start with ax. Ax is given by the formula. Ax is equal to u dou u by dou x plus v dou u by dou y plus w dou u by dou z plus dou u by dou t. Now the values of u, v and w are known to us. U is 4x cube, v is minus 10x squared y and w is 2t. So let's start first with the differential terms dou u by dou x and find out what they are. So dou u by dou x, u is 4x cube. So dou u by dou x is given by 4x cube, dou of 4x cube by dou x. So if we take this differential, the 4x cube term contains only x, and so it's easy to differentiate this. This will become equal to 12x squared. So dou u by dou x term is known to us. Now dou u by dou y. So we're going to differentiate dou u with respect to dou y. This is dou by dou y of 4x cube. Now what we have to remember here is that partial differentiation, when we are doing partial differentiation, the function is going to be differentiated with respect, partially with respect to a variable. So 4x cube is going to get differentiated with respect to y. When you are partially differentiating with respect to a variable, for example here we are partially differentiating with respect to y, what we have to understand is that only if there is a y term in this expression will it be considered. Any other variable or number or any other function that is there will be considered as a constant. So if a y term comes here, it will be differentiated. Otherwise, everything else remains a constant and will not be recognized by this differentiation. So according to dou by dou y of 4x cube, according to the partial differentiation with respect to y, 4x cube is a constant term because it does not contain y term anywhere. And so 4x cube is taken to be a constant and differential of a constant will be equal to 0. So only if a y term is there, this differentiation, this differential will recognize it. Otherwise, it will consider it as a constant and equate it to 0. Dou u by dou z. So here 4x cube is differentiated partially with respect to z. So when you're differentiating partially with respect to z, if a z term comes here in the expression, it will be considered. Otherwise, this whole term will become a constant and differential of a constant will be equal to 0. Similarly, dou u by dou t, again 4x cube differentiated partially with respect to t. There is no t term in the expression, and so dou u by dou t also will be equal to 0. Since we have found out the values of dou u by dou x, dou u by dou y, dou u by dou z and dou u by dou t, we can put it back in the expression for ax. Since dou u by dou y, dou u by dou z and dou u by dou t are 0, these terms need not be considered. We need to consider ourselves only with u dou u by dou x. And so ax will become 4x cube into 12x squared. U dou u by dou x. This becomes 48x raised to 5. At the point 2, 1, 3 and t equal to 1, ax is given by 48 into 2 raised to 5, which is 1536 units. You can see here that I have not mentioned any units as in meter squared per second or kilometer squared per hour or nothing like that. This is because the dimensions have not been mentioned in the problem also. So I'm not sure which particular dimension they are mentioning. I'm not sure if it is kilometers or meters or miles or inches or what is it that they have actually given the velocity in. So in order to avoid confusion, I will simply write the unit of AX as 1536 units. Now to find out AY and AZ in a similar fashion. AY is given by this expression U dou V by dou X plus V dou V by dou Y plus W dou V by dou Z plus dou V by dou T. So V is getting partially differentiated everywhere. And we know that U, V and W are given by these terms. So first we'll start with dou V by dou X, dou V by dou Y, dou V by dou Z and dou V by dou T. Dou V by dou X is dou by dou X of minus 10x squared Y. So since an X term is coming here, that will be differentiated. Minus 10y is considered as a constant. So we'll get minus 10y into 2x, that is minus 20xy. When you are doing dou V by dou Y, again minus 10x squared y. Here y is the only variable. Minus 10x squared is considered as a constant. It will come outside. And thus dou V by dou Y will become simply minus 10x squared. When we are talking about dou V by dou Z, there is no Z term here. So the whole thing is considered to be a constant. And so dou V by dou Z is 0. And when considering dou V by dou T, similarly, since no T term is available, dou V by dou T is also 0. So we have only dou V by dou X and dou V by dou Y here with us for us to substitute. So these two terms will be active. These two terms will go to 0. And so we are going to substitute in the expression for AY. And we will get 20 x raised 4 times Y. At the point 2, 1, 3 and T equal to 1, we will obtain AY to be equal to 20 into 2 raised to 4 into 1, which is 320 units. Now AZ. AZ is U dou W by dou X plus V dou W by dou Y plus W dou W by dou Z plus dou W by dou T. U, V and W are known to us. Now for partial differentiation, we need to consider only W over here. Dou W by dou X is dou of 2T by dou X. So the variable inside W is actually T. And when you're partially differentiating with respect to X, this whole thing will be considered as a constant. And dou W by dou X would be 0. Similarly, dou W by dou Y would be 0. Dou W by dou Z would also be 0. But dou W by dou T would be equal to 2. Because here there is a variable T in the expression. And so you don't have much to do. AZ would be given by simply dou W by dou T because all the other terms are going to 0. And so AZ would be 2 units. Now to find out the resultant acceleration. AX is known, AY is known, AZ is known. Resultant acceleration square root of AX squared plus AY squared plus AZ squared. Substituting, you will get the resultant acceleration as 1568.98 units. So this is the next numerical problem. Again, a very similar numerical problem. If you want, since you already understood how it is to be done, you can pause the video and do this problem on your own. Velocity vector is given by x squared y I cap plus y squared z j cap minus 2xyz plus yz squared k cap. And find the velocity and the acceleration of the particle at the point 2, 1, 3. So this is the value of velocity. U is x squared y, v is y squared z, and w is minus of 2xyz plus yz squared. So at the point 2, 1, 3, we will obtain u to be equal to x squared y, that is 2 squared into 1, which is 4. V is equal to 1 squared into 3, y squared z, which is 3. And w is equal to minus of 2xyz plus yz squared, which on substitution will get minus 21. And so the resultant velocity, which is square root of u squared plus v squared plus w squared, can be obtained as square root of 4 squared plus 3 squared plus minus 21 the whole square, which is 21.587 units. Now, to determine the acceleration, AX is given by U dou U by dou X plus V dou U by dou Y plus W dou U by dou Z plus dou U by dou T. So U, V and W are known to us. We'll differentiate U this time. partially with respect to x, y, z and t. Dou u by dou x is dou of x squared y by dou x. Since x term is there, it does not go to 0, it will become 2xy. Dou u by dou y again, since y term is there, this dou by dou y of x squared y is the only variable that is considered, the others are considered as constant. So dou of x squared y by dou y will become x squared. Dou u by dou z as well as dou u by dou t will go to 0 because there is no z or t terms in u. So substituting the values in the expression for ax, we will obtain, and substituting the coordinates 2, 1, 3, we will obtain ax as equal to 28 units. So next is ay. And ay is given by u dou v by dou x plus v dou v by dou y plus w dou v by dou z plus dou v by dou t. So here the partial differential is taken for variable v, and v is given by y squared z. So finding out the partial derivatives, dou v by dou x is dou by dou x of y squared z. Since there is no x term here, the whole thing is considered to be a constant. Dou v by dou x becomes equal to 0. Dou v by dou y is dou by dou y of y squared z. Y squared is there, and so it will be differentiated. Z is considered as a constant, so 2yz. Dou v by dou z is dou by dou z of y squared z. Z is considered as the variable, y squared is considered as a constant, and so dou v by dou z would be simply y squared. Dou v by dou t would go to 0 as there is no dependency on time t. Substituting this in the expression for ay, we would obtain ay is equal to y squared z into 2yz minus 2xyz plus y squared into yz squared into y squared. So we will end up with a polynomial y cube z squared minus 2xy cube z. Substituting the point 2, 1, 3, we would obtain ay to be equal to minus 3 units. So next is az. Az is u dou w by dou x plus v dou w by dou y plus w dou w by dou z plus dou w by dou t. U, v and w are given to us. Now dou w by dou x would be, since w is minus of 2xyz plus yz squared, dou w by dou x would be minus 2yz. So I am directly writing the value for this. That is another way of doing this. Since the coordinates 2, 1, 3 are known, we can find out the value of dou w by dou x at that particular point, which is minus 2 into 1 into 3, which is minus 6. This will help us to reduce the amount of polynomial multiplication we have to do at the end. Dou w by dou y, if we are doing, would be equal to minus 2xz plus z squared, minus z squared, and that would come to minus of 21 on substitution of the point 2, 1, 3. Dou w by dou z would become minus 2xy minus 2yz, which would be on substitution equal to minus 10. Dou w by dou t would be 0 since there is no t term in the expression. So the numerical values are already known, and u, v and w numerical values are also known to us. Or we can substitute x squared y as 2 squared into 1, v would be 1 squared into 3, and w correspondingly, so that we can simply multiply numbers instead of multiplying polynomials and making careless mistakes. So az would be x squared y into minus 6 plus y squared z into minus 21 plus minus 2xyz minus yz squared into minus 10. Substituting at the point 2, 1, 3, az would be 4 into minus 6 plus 3 into minus 21 plus minus 21 into minus 10, which would come to 123 units. So always this way is much more efficient corresponding to the previous ways in which we were multiplying polynomials. When we directly substitute and obtain the numerical values, the amount of multiplication involved reduces. So here we have ax, ay and az as 28 units, minus 3 units and 123 units. Resultant acceleration is square root of ax squared plus ay squared plus az squared. And on doing this operation, we end up getting the resultant acceleration as 126.182 units. Next, we are going to discuss continuity equation of fluid flow. So fluid flow needs to be continuous, that is, the mass of fluid going in should be equal to the mass of the fluid coming out. So this is basically law of conservation of mass. So the mathematical condition that we are going to develop for continuity of flow is known as the continuity equation. So let us consider a fluid element. Let this be a fluid element, a cuboid shaped fluid element. These are the coordinates or the axis of the fluid element. I have drawn the x-axis, y-axis and z-axis on the fluid element denoting the direction of flow. Consider a fluid element of lengths dx, dy and dz. So these are the lengths dx in the x direction, dy in the y direction and dz in the z direction. So the volume of the fluid element would be dx, dy, dz. Let u, v and w be the components of velocity in the x, y and z directions. So here let us consider the flow happening in the x direction. Okay, now when the flow enters the control volume, it is going to enter through this particular shaded area, which is equal to dy into dz. So mass of the fluid entering the fluid element in the x direction per second is given by dm by time, which is density into d volume. That dv is the volume of the element by time. So that would be rho into dx, dy, dz by time. Since we are considering the mass of fluid entering in the x direction, dx by t can be taken to be the velocity in the x direction, which is u. So the mass of the fluid entering per second in the x direction is given by rho into u into dy dz, because dx by t can be taken to be equal to u. This is the mass of the fluid entering the fluid in the x direction per second. Now the rate of increase of mass with distance. So what is the rate at which mass, let us assume, usually we know that mass is not going to increase in the as the fluid is traveling through the control volume. However, let us assume that mass increases as it passes through the control volume. That is, with each step it takes, with the distance it is covering, its mass is increasing. We are assuming this. Now why we are assuming this, you will understand later on. We are assuming that the mass of the fluid is going to keep on increasing as it moves forward. Then the rate of increase of mass in the x with distance in the x direction would be given by dou x of the mass of fluid that has flown into the control volume. So dou x of rho u into dy dz is the rate at which the mass of the fluid is going to increase with distance. So what would be the mass of the fluid that is going to leave in the x direction? So it is leaving through this phase. It had entered through this phase and it is now leaving through this phase. If we want to calculate the mass of the fluid leaving in the x direction, it would be the initial mass plus the amount of increased mass. And so that would be rho u into dy dz plus dou x of rho u into dy dz into dx. How we obtain this? Dou x of rho u dy dz is the rate at which the mass is increasing with distance. And the distance traveled by the fluid is equal to dx in the x direction. So the total increase in mass would be dou x of rho u into dy dz into dx. So this is the total mass of fluid that is going to leave through this phase in the x direction. So the net gain of mass in the x direction is given by simply dou x of rho u into dy dz into dx. This much amount has increased. When it initially entered and finally left, the amount of increase of net gain of mass as it was inside the control volume in the x direction is given by dou x of rho u dy dz into dx. Now similar calculations can be done for fluid entering in the y direction as well as fluid entering in the z direction. So the net gain of mass in the y direction can be obtained as dou y of rho v into dx dz into dy. All this is analogous to the previous expression that we had obtained for net gain of mass in the x direction. Similarly, net gain of mass in the z direction is given by dou z of rho w into dx dy into dz. If you want, you can follow the same procedure that was followed for flow in the x direction to find out the net gain of mass in the y direction and z direction. Now, fluid mass does not increase with space alone. It also is bound to increase with time, or we are assuming that it also increases with time. So with time it increases as dou m by dou t or dou by dou t of rho into dv. Mass is given by density into volume, so rho into dv by dou t. Rho is not, we cannot assume that rho is a constant immediately, because we have studied about, or we have learned about compressible flows where rho cannot be a constant. So rho is still inside the bracket. The volume dV is given by dx dy dz. So that would be dou rho by dou t into dx dy dz, because dx dy and dz are constants. They are the dimensions of the fluid element. The net increase of mass in the fluid element is given by the increase of mass in the x direction plus the increase of mass in the y direction plus increase of mass in the z direction plus increase of mass with time. This is the net increase of mass in the fluid element. However, by the law of conservation of mass, we know that when water enters the control volume, it does not gain any mass before it leaves the control volume. And so, net increase of mass of a fluid as it passes through the control volume is equal to 0. And so this whole expression that we have obtained as the net increase of mass in a fluid element can be equated to 0. Thus, dou by dou x of rho u dy dz into dx plus dou by dou y of rho v dx dz into dy plus dou by dou z of rho w dx dy into dz plus dou rho by dou t into dx dy dz is equal to 0. You can see that dx, dy and dz are common throughout, and they are also constants, and so they can be cancelled. And our expression will now read dou of rho u by dou x plus dou of rho v by dou y plus dou of rho w by dou z plus dou rho by dou t is equal to 0. This is your continuity equation. This is the expression for continuity equation. Now, from this expression for continuity equation, we can say that for steady flow, if the flow is steady, then none of the properties would change with respect to time. That is, this term dou rho by dou t will not exist, as this will go to 0. For a steady flow, it is time invariant. That is, time is not a factor on which the properties change. So dou by dou t of a property would become 0. So if the flow was steady, dou rho by dou t would have been 0, and we would have ended with dou rho u by dou x plus dou rho v by dou y plus dou rho w by dou z is equal to 0. This is the continuity equation for steady flow. Again, if the flow was incompressible, then density would have been a constant. If density was a constant, it can be taken out of the differential sign. So when we take density out of the differential sign, we will get rho dou u by dou x plus rho dou v by dou y plus rho dou w by dou z is equal to 0. Rho is constant, it can be cancelled off, and we will get dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So for a steady incompressible flow, continuity equation is dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. This is continuity equation for three-dimensional flow. If the flow that we had considered was two-dimensional, it would have simply been dou u by dou x plus dou v by dou y equal to 0. That is, the w component would not have been there in two dimension. And for one-dimensional flow, it would simply have been dou u by dou x is equal to 0. So these are continuity equations in 3 dimensions, 2 dimensions, and 1 dimensions for you. Moving on to some numerical problems. It's given that the following cases represent the two velocity components of a 3-dimensional flow. Determine the third velocity component such that it satisfies the continuity equation. So there are two questions here. First question, v and w are known, u is unknown. And the second question, u and v are known, w is unknown. So using continuity equation, we have to find out the third component. So let's start. So the first question was given as v equal to 2y squared, w equal to 2xyz, and u equal to unknown. We know that from continuity equation, dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So we don't know u, but dou v by dou y and dou w by dou z can be found out. So dou v by dou y is nothing but dou of 2y squared by dou y. Since it's a variable in y, it can be differentiated partially with respect to dou y, and it will become 4y. When you're talking about dou w by dou z, there is a z term here which can be considered as a variable and the others as a constant. So dou w by dou z would be given as simply 2xy, which means that substituting it back in the continuity equation, we will obtain dou u by dou x plus 4y plus 2xy is equal to 0. or we will get dou u by dou x is equal to minus 4y minus 2xy. All we now need to do is integrate. But let us not forget that when we are integrating, we are actually integrating for a partial differential. So u would become minus 4xy minus x squared y plus a constant of integration. This part seems simple enough. But the catch in this problem is that what is this constant of integration? Is it a constant? It's a number? Is it a value? Or is it a function? Since u is partially differentiated with respect to x, anything that does not contain an x in it can be considered as a constant. As far as dou u by dou x is concerned, anything that does not contain an x in it can be considered as a constant. And so this particular c value over here can actually be a function of y and z, could actually be a function of y and z and still be considered as a constant. And so c is a function of y comma z and u can be obtained as minus 4xy minus x squared y plus a function of y comma z. If you want to check dou u by dou x, you can find out dou u by dou x would be minus 4y minus 2xy plus 0. And that is exactly what you obtained here. So in the second problem, u and v are given and w has to be found out, and we know that it satisfies the continuity equation. So according to the continuity equation, dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. And since u and v are known, dou u by dou x and dou v by dou y can be easily found out. So first we'll find out dou u by dou x. So here x squared plus y squared plus z squared, x squared is the only term that consists of an x. All the others are considered as constants. And so dou u by dou x would become equal to 2x. Dou v by dou y, on the other hand, each term consists of a y. And so all these terms can be considered for differentiation. So it will become 2xy minus z squared plus x. So this is dou v by dou y. Now, dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. So adding up, we will get dou w by dou z is equal to minus 3x minus 2xy plus z squared. It's a partial derivative with respect to z. So integrating, we will get w to be minus 3xz minus 2xyz plus z cubed by 3 plus a constant of integration. Now this constant of integration is important. It's not it need not simply be a number. It can be a function. So since when w is partially differentiated with respect to z, any function of x and y can be considered as a constant. So this c could be as well be a term like xy or x squared y or x cubed y raised to 4. And it would still be differentiated and it will still go to 0 for dou w by dou z. So c could be a function of x and y. And so w can be written as minus 3xz minus 2xyz plus z cubed by 3 plus a function of x comma y. So this constant of integration can be written as a function of x comma y. Now if you want to check, we can check dou w by dou z. We can check whether we are getting the same expression, minus 3x minus 2xy plus z squared. Dou w by dou z, so minus 3x minus 2xy plus z squared. And this term when differentiated with respect to z partially would go to 0. And this is how numerical problems on continuity equation can be solved. Other problems like check whether the flow is steady and incompressible and such can come, over where you have to apply the continuity equation and check whether dou u by dou x plus dou v by dou y plus dou w by dou z goes to 0. So I hope that the kinematics of fluid PPT has been a useful one, that you understood the concepts and you would be able to attempt problems that now come from this topic.